Last time we started an example of gradient descent search for a quadratic function, and today we're going to finish that off. So we did the first step, if you like, of the gradient descent search, and then we're going to do a second step. And what we're going to find is that the directions of gradient descent search are perpendicular. That's a key result today, and I'll then give a proof of short proof of why that is. Okay, so I just want to draw your attention to the lecture notes for this function that we're trying to minimize. This is a contour plot of the function that we looked at last time, and we established last time that the minimum was at a point 1/3, 4/3. I think we asked last time. And what we did is we started off our algorithm at point 3, 0, and we then constructed the gradient, which took us this way. Let me just take the bits off from there. So it took us this way, and then we stopped the trajectory there. So end of last time, we started off at x1 at that point there, and we went to x2, next point there. So the next thing to do is just to do the next step, and construct that and see how well our gradient descent takes us towards the minimum. That's the first step we did last time. Now we're going to do and find where x3 is. So the next thing is, where is x3? Okay. Let's go back to the board. So I guess you're going to do now our second iteration. What we're going to do is construct our second search direction. S was for search direction, and remember it's in the negative grad f direction. It's down the gradient of the function, but you have the freedom to scale it by whatever you want. In this case, 4 turns out to be a good value, and this grad function is evaluated at x2. So remember, x2 is simply 1, 0. It's that second position we got to. So you're just plugging, when you plug a vector into the function like this, you're essentially plugging x is 1 and y is 0, and this is a very efficient way of sort of expressing that. Okay, so when you do plug that in, you get -1/4, putting x is 1, y is 0 in to the gradient that we had before, gives 4x plus 2y, and y is 0 minus 4. And then it's 2 minus 6, and that equals, let's just take that other loop a minute, that equals 0, 1. So that's interesting, because our first search direction was this way, was -1, 0. Now the second search direction, this way. You may notice they're perpendicular, and that is a feature of gradient descent. So gradient descent directions are perpendicular, and there's a little proof of that in the lecture notes that I hope to get to. But that we're just sort of observing it at the moment, that if the first direction is that way and the second direction is that way. If we just go back to our function, then we've taken our initial trajectory here. This was S1, and then S2 is up here, and I think we're beginning to see now the weakness of gradient descent, because really we want to go straight onto the minimum, but because this method is constrained by going in perpendicular directions, it will never quite reach it. It'll get close, and that's where we're working with. But let's just continue working through on the board. So we can now say that the inner product of S1 and S2, which remember is a dot product, is this. I.e. S1 and S2 are perpendicular, orthogonal, perpendicular. So we've got this new search direction, so we can now write down our trajectory step, and this will take us, x3 is x2, and I'm just going to write this as alpha, and write alpha 2 as alpha, just for convenience, ease of sort of expression. So basically we're starting at x2, we're going in the direction of s2 direction, and we've got our trajectory length alpha that we need to determine by minimization. So that's our trajectory. Let's just plug the numbers in. So x2 was 0. No, it wasn't. It was 1, 0. And S2 is 0, 1, and it's multiplied by alpha, so we get alpha. So the vector is 1 alpha. That's S3. Just write it up in the new page. X3 equals 1 alpha. And then we substitute x3 into f and minimize with respect to alpha, our trajectory length. So what we're interested in is d by d alpha of f on x3 and this is probably the trickiest stage, and obviously this is minimization, so it's 0 on that minimization. So we expect a function of alpha in there, and so let's just write that up at the top. Remember, what we're doing all the time is we constructed a trajectory across this function with ending at x3, starting at x2, and rather than minimizing the function anywhere, we're minimizing it along this trajectory. So we're minimizing along the trajectory. And we're minimizing with respect to alpha. So we've got to remind ourselves what f is. Well, f of x vector is 2x squared plus 2xy plus 2y squared minus 4x minus 6y. And because x3 is 1 alpha 2, all we're doing then is substituting x equals 1 and y equals alpha 2 into it. Actually, we're dropping the alpha 2s, aren't we? And we've just got alphas, x, y into this expression, and then differentiating with respect to alpha. So we end up with d by d alpha. So remember, x is 1, y is alpha, plus 2xy gives us 2 alpha, plus 2y squared gives us 2 alpha squared, minus 4x is minus 4, and minus 6y is 6 alpha. That's what it is. And then we've reduced it down to actually a simple calculus problem. We know how to differentiate that very easily. But it's just remembering what the function is, remembering what your end point of your trajectory is, substituting one in the other and then differentiating. Okay, so you could, if you wanted to break this down further, you could do that substitution into f of x first, which is kind of what I've done in the contents of this brackets, and then differentiate with respect to alpha. I'm just going to rewrite things today. In fact, really, it should be vertical, these on here, because we've only got one function. So we've got, let's do that. So we've got d by d alpha 2 plus 2 alpha plus 2 alpha squared. That's 4 minus 6 alpha equals 0. So the 2 and the 4 just go to 0. Easy, can that? So we then have 2 plus 4 alpha minus 6. And then obviously the 2 and the 6 cancel, which equals 4 alpha minus 4 equals 0. So implies, let's put some implies here, alpha equals 1. And alpha equals alpha 2. It's just a relabeling of that. Okay. So this is a sort of repetition of the whole process. You construct the trajectory based on the gradient. You minimize along the trajectory to find out how long that trajectory should be. You stop and redo everything again. So it's an algorithm really set up for computers. So what we now need to do is to substitute alpha into x3. And we have then x3 equals 1 alpha 2, which equals 1 1. And that's where we're going to stop it. We're just going to do 2 steps. We're not going to torture ourselves. We'll just do enough steps to understand how the method will work. So if we go further down the notes, there's a plot then somewhere. Forget about the red line at the moment, but how these first 2 steps of the gradient descent work. So this is a position vector x1. So it's getting used to using vectors as a position vector, something you should be familiar with. So we start at x1, go to x2, then to x3, and if we were to carry on, it would just be perpendicular directions. And I just want to outline the steps that how you can prove that the successive directions are perpendicular, because it has to do with the fundamental way in which the method is set up. So y directions perpendicular. So this is page 70 of the lecture notes as I have them. So we're going to go back to the more general statement of the gradient descent in terms of just without making the substitution for search directions, because we're just interested in how the method works. So this is our trajectory now. I'm just going to write down a trajectory. So a new value of x is our old value minus some trajectory length times grad f at x of n. So we've got a trajectory. So this is a more general statement of your gradient descent search. We're starting at x of n. We're going to x of n plus 1. we've got the gradient there. So if you differentiate this expression, first thing we have is if we differentiate xn plus 1 with respect to lambda, you can just xn is fixed as far as we're concerned with this derivative, so you making derivative of this thing, and grad f of x of n is fixed for that given trajectory, so it's simply minus grad f of x of n, and we'll use that again. Basically the gradient is telling us, basically is saying that the increment of xn plus 1 at the end is in the direction of minus grad f of xn, which is the method, entirely the way the method is set up. So that's the first thing. And then, so that's from the trajectory. And then we have the minimization. So basically then we're considering x of n, xn plus 1, and we're considering little changes in our vector dx of n plus 1. So what we're going to say is what we're going to look at is what's the change of the function for that change along the trajectory. So we have dx, and we're going to have d of f at xn plus 1. These are changes in the function and changes in the trajectory. In that case, we can write df equals grad f at the end point now, times by dxn plus 1. That's basically just your basic calculus here. It's saying the change of a function is the first derivative times the increment, and that's at the xn plus 1. And if we then differentiate that, we have that partial f by at x of n plus 1 by d lambda n equals grad f of x of n plus 1 partial xn plus 1 by d lambda n, and it's this thing that we derived earlier from the trajectory. So it's all laid out in the lecture notes if you want a sort of clarification of where we're going. But we also know that that is our statement of our minimization. So let's just write that out again. So we've got d by d lambda n of our function at the end of the trajectory equals the gradient at the end of the trajectory. So that should be transposed. I think I lost that before. Times partial x n plus 1. Because we're doing this quite generally for the moment, it seems a little bit more abstract, but it's the best way. We want to show is that this feature of minimizing along a trajectory defined by the gradient is, but that equals 0, you see, because that's your minimization. Yeah, that's the d by d lambda n function at the end equals 0 is exactly your definition of minimization. So then we substitute for dxn plus 1 d lambda n. Remember this thing here equals minus grad of f of x of n at the start of the trajectory. So we then end up with expression, we substitute minus grad of f of x of n, we end up with minus grad of f of x n plus 1 transposed times grad of f of x xn is 0, which is exactly your perpendicularity relationship that we saw for the specific case, but this is showing more generally that works. So i.e. successive gradients are perpendicular. Okay, so all we've done is we've written down the general form of the trajectory and gradient descent. Then used the minimization criterion as well, combined with a little bit of calculus using these vector quantities, and we end up with the result that because we're constructed the method in this way, we're moving along the gradient, and because we're minimizing along that trajectory, it's hardwired that the successive directions are going to be perpendicular. Okay. And we'll stop there. See you next time.